So now sort of we let's start with the doing the recursive part, right? So we sort of want to say imagine that we can sort of like put this subproblem in this manner: x1 up to xi, right? So I'm drawing over here, and y1 up to yj, right? So now, we sort of want to make a decision, right? So this is the optimal solution we are trying to look for, right? So, we sort of want to make a decision, right? Just imagine, just recall that we sort of want to decide the alignment, right? So what is the alignment? Alignment is really just that whether we want to determine the how can I match xi with the yj, those kind of things, right? So for each of the x, we sort of want to either make a matching or really just decide to skip that, right? So now there are a number of cases here, right? So the first case would be just in the optimum solution, right? So imagine that the optimum solution, just that xi maps is matched with yj, right? So this is the first case. In the optimal solution, xi and yj is matched, right? So now, so after this, after if this case were true, then what we have to do is that we pay the mismatch cost for xi versus matched with yj, right? So just pay attention here. This is not minus, right? So this is the match, right? So we pay a cost of xi match the yj, and then we want to solve the subproblem. So let me just erase that a little bit, right? So the subproblem we are talking about here is that now xi and yj's are matched. So then the subproblem we want to solve is really just x1 up to xi minus 1 matched with trying to align with the y1 up to yj minus 1, right? So this is the first case. These two letters are matched, right? The the second case would be just that we sort of want to leave xi unmatched, right? So basically, I want to get rid of xi and then really just use the subproblem of x1 up to xi minus 1 to sort of trying to match with y1 up to yj, right? So in this case, then we have a different kind of cost, right? Because xi is not matched with y, any of the y, so there's a gap cost here. And after that, we really just, as I mentioned, I draw here, I sort of want to try to solve the subproblem of matching x1 up to xi minus 1. And for y, then we are not going to need to sort of touch this y, right? It's still y1 up to yj, right? So this is the second cases, right? So I leave xi unmatched, and the optimal solution is really just I minus 1 and j, right? So this is the second case. And the third case would really just be that by symmetrics, we can also leave yj unmatched, right? In this case, there's a gap cost, right? So I just get rid of this one. Instead, I'm just going to match this one in the subproblem, which this one was this one. So this is x1 up to xi. This is y1 up to yj minus 1, right? So this is this one, trying to minimum alignment cost of this part, and then there's a gap cost. That's the same as the second case, right? So this would be the recursive, right? In case, right, one of them is 0. So basically, in case we are trying to solve some problems like opt I 0 or opt ZOJ, right? So basically, we only have the gap cost. Like in this case, like these are really the base cases, either I equal to 0 or J equal to 0. They are only base cost, gap cost, right? So after we set up the entire recursive form, then basically we are we are getting very close to review the final answers, right? So basically, we want to build up one more layers of the memorizations, right? Our memorization, we still use the M matrix, right? So there's an M matrix here, right? So this is 1 up to N, this is 1 up to, this is N, right? So this is the matrix we are holding here is serve as a cache purpose, right? So if what the meaning, we sort of want to fill in Mij as the opt ij, right? So again, that we can sort of use the recursive top-down approach, and this algorithm here is really just showing the bottom-up approach, right? You scan from left to right, from top to bottom, and and we are able to whenever we want to fill in an entry here, right? So if we want to fill in the mij here, right? mj, so this is equivalent to computing opt ij, right? So this kind of recursive really guarantees that my search directions are really just moving towards this direction, or this direction. So long as if all the values of this particular regions are filled in, then this particular elements can be filled in, right? Can be filled in when the red elements are filled in, right? So that's the reason that if we scan from left to right, top to bottom, we don't run into any dependency problem. We can easily really just copy and paste the entire thing here to really compute the value of mij, which is the same as the value of opt ij, right? So this is the final solution, and basically this is again the idea here is really just that we now have a two-dimensional settings, right? So in the knapsack problem, we sort of saw the first of two-dimensional table. Now this is the second two-dimensional table, and we sort of have like the number of operation here is also a bit more complex than the knapsack problem, right? But otherwise, I think the principles remains the same. After you see so many problems, you can sort of start to have a feeling of So after we sort of see the pseudocode, the only thing we need to be careful is that how do we recover the alignment problem, alignment solution, right? So basically, it's really just a backtracking. I think this one can be left for you to understand. Once you get the optimum solution, how can you backtrack and find the optimum solution? And actually, I think one of the homework's problems is going to be about this problem. Right. So we don't need to look at, so the results pretty straightforward, right? So basically the running time and the space complexity is both in the order of m times n. Right. So we will just skip this algorithm and we will directly move to the Bellman-Ford algorithm. So skip. No. So now we are at the Bellman-Ford algorithm, right? So recall that we do want to find the shortest path. So recall that we do have a shortest path problem, right? So in the shortest path problem, we are given a directed graph that's consists of the edges and vertices, and we have arbitrary edge lengths, right? So we sometimes call that weights in our previous lectures. And we want to be able to find the shortest path from the source node to the destination T, right? So this is the source S, and this is the destination T, right? So here for the conceptual, just for for getting the most important concept out, right now we really just want to find the shortest path between two specific nodes. Although at the end of the day, we are able to find the shortest path between all pairs of nodes. Right. So for this particular example, so just look at this whole graph, right? So the only difference between the shortest path that's given, between the graph that's given here and the graph we have been studying is that there exists a number of like negative weights, right? So, and also it turns out that when we run the shortest path algorithm, we are able to the actual solution consists of two edges that have negative weights. So before we proceed to understand how we can use DP to solve this problem, we really just want to play a bit and see whether there's any straightforward method that can help us to solve the problem, right? So the first thing is that if you run Dijkstra, and basically as a matter of fact, it's actually not able to give you the shortest path when the edge weights can be negative. For instance, if we run the Dijkstra on this graph, right? So this is starting from S. In the very first step, what it is going to claim is that it's going to look into all its neighbors, the neighbors T and V, and So just recall that we associate each of the node with the function pi, right? So the pi of t after the first step is going to be 2, the pi of v after the first step is going to be 6, right? And as well as the w, right? The pi of w is also going to be has the value of 4, right? So now in the next step of the shortest path, the Dijkstra algorithm, we just look at all these three numbers and pull out the smallest number, right? So what's going to happen is that we are going to claim that we have already found the shortest path from S to T, and the shortest path is 2, right? So and then we are really just going to remember that the shortest path is really partitioning at any moment is going to partition the whole graph into those that are already explored and those that are not yet explored, right? So after the first step, we are actually immediately going to call these two nodes to be explored, and we are not going to reconsider T anymore. But on the other hand, if you look at the actual shortest path that's moving from S to T, it's actually taking a very long route, right? So it's from S to V, V to W, W to V, right? So to T, right? The actual shortest path the actual value is going to be 1, right? Which is actually, if I sum up all these three numbers, 6 minus a plus 3 is going to be 1, right? So this is actually a number that's much better than what we have found, right, by using the Dijkstra, right? So the main question here is that the Dijkstra didn't anticipate that there's some sort of negative weights over here. So if we were replacing these negative weights by 1, there's no way of making this path to be longer than 2, and then the Dijkstra in that case would be correct. But unfortunately, we do have the negative weights, and because of this kind of negative weights, Dijkstra is actually giving a wrong solution between S and T. It didn't find the shortest path, right? So this is actually a very straightforward observation that Dijkstra doesn't work. And as a computer scientist, one of the very good habits is to really to understand whether we are able to just tweak the original problem, right? Let me just erase everything here. Let's see. So now for the entire graph, right, there's only one edge that has negative weights, right? So one intuitive way of tweaking the graph is say, why don't we just add 8, right? Just make some sort of shifting of all the weights, right? So let's shift all the weights by number 8, right? In this case, this weight over here, it becomes non-negative again, right? So we actually come up with this graph, right? After we come up with this graph, we sort of hope that, right, we were sort of hoping that can we reduce, right? That's the question we have here, right? Can we reduce the problem with negative weights, weights to a problem without negative weights. This is really the attempt we are making, and the way of trying to do that. One intuitive way is really just to offset all the numbers so that the smallest number is going to be 0, right? After we do the offsetting, we can try again to run the shortest path algorithm, and we sort of realize that again we found the wrong path, right? So this is the path we found after the shifting, right? We still found the S to T, right? The real question here is that if you have two paths, right? So if you have two paths, that has the same number of edges connecting from S to T, right? So if you have two passes, P1 and P2, right? This is P1 and this is P2, right? If two passes have the same number of edges, right? If we add the same constant to every single edge, then of course, like these two passes are going to be shifted by the same amount of values, right? So in this case, right? So before adding 8 and after adding 8, right? The length of these two passes in terms of the orders would be the same, right? So for example, originally the weight of P1 probably is 10, the weight of P2 is 5, right? This is the originally what's going to happen, right? And after we do this, adding this 8, then sort of we get the new weight to be the 10 plus 8 times 3, and the new weight of P2 is going to be 5 times 8.3, right? So this is how the number comes from. So this is original weight, 10 and 5. 10 move to here, 5 move to here. And then we sort of are adding 8 in every single pass, right? So in this case, it both adds 28, right? So if originally the first pass is longer, and then in the new, after we update the weight, the first pass is longer, still longer, right? This reverses the intuition of trying to offset the weights. But in case if we have two passes that have different number of edges, right, then we sort of realize that this method doesn't work, right? So in this case, if we look at the first pass, it's going to be incremented. The delta is going to be 26, 4, right? The increment, the amount of increment after this offsetting is going to be 3 times 8, right? But if we are looking at the second pass, the amount of increments is going to be 2 times 8 is 16, right? So it has different kind of different incremented values for different passes if they have. What's more nasty here is that besides that sometimes the shortest path actually contains a negative weight, edge with negative weights. What's even more nasty is the presence of the possibility of the negative cycle, right? So so let's really just define the negative cycle. A negative cycle is the directed cycle. When we sum up all the edge weights, the cycle is the sum is negative, right? And if you look at this particular example, the cycle over here, it's a negative cycle, right? The reason is that if I look at the 5 minus 3 minus 4, right? This is minus 4, this is plus 4 minus 3, right? So this is 5 here, 3 here, 4 here, 4 here, and minus 3 here, right? So I will get a negative 2, right? So the whole cycle is negative 2, right? What does that really mean, right? That really means that, for instance, if so there's a pathological case that's presented here, right? So if I want to find the shortest path between S, and let's call this number V, right? So what I'm going to do is actually I'm going to just keep looping, right? I'm going to loop once and loop second times and loop, right? So basically I'm going to travel from S to V and back to S, back to V, back to S, back to V, right? I can just keep doing these things, and every time I go back to S, my path length is going to be negative 2, and this is going to be negative 2, and so on and so forth, right? So I keep doing the same thing until infinite amount of time. Then basically we're going to get the shortest path. We're going to get a path that's connecting from S to V with negative infinite weights, right? So so basically the intuition is really just that we are the algorithm is too attracted by this particular negative weights loop. It will just keep using the loop to try to reduce the total path length, and then this algorithm will be trapped into the just using this loop, right? So so this is a better visualization here, right? So imagine we do want to travel from V to T, right? If there's a negative negative weight cycle that's passing through a particular node over here, let's call this node S, right? Then we can just keep running. When we construct the shortest path in this manner, right, from V to S, and travel again, then if we travel multiple, like infinite number of times, then basically the whole path over here is going to be negative infinite, right? So we sort of want to say that this is not really a well-defined problem, right? So let's also look at what this lemma talks about, right? So if there exists some path, if for some path that contains a negative cycle, then there does not exist a shortest path, right? So we somehow say that when we just keep using this loop, we will have shortest path that has infinite weights, right? So basically that just means that this process won't stop, and mathematically speaking, then that's more or less equivalent to that we are never able to find the shortest path, right? Whenever we find a path that's small enough, we use this negative cycle again and get a number that's even smaller, right? This process just will not terminate, right? This is the first dilemma, right? And let's say that if you are sort of living in a little bit more benign world where if I can guarantee, like imagine a simpler word, that we can guarantee uh, that there's exists no negative cycle. Then we also have another important lemma that basically says that if G has no negative cycle, then there exists a shortest path that is simple. Right? Just recall that what is simple. Simple means that no node appeared twice. Right? So simple also intuitively means that the whole path doesn't contain a cycle. Does not contain a cycle, right? So this path over here, right? So the path over here, the step 1, step 2, and step 3, right? This is an example. So 1, 2, 3. This is an example of non-simple path, right? Right. So the argument here is really just that the key message here is that like in case if you are guaranteed that the graph doesn't have any negative cycle, and somehow if the algorithm somehow decides that if I want to find the shortest path between V and T, and somehow the algorithm claims it's the shortest path, and you find a cycle that's here, right? So in case, right? So in case, just assume that an algo give you a non-simple path, right? So assume that there's a cycle that looks like that. Then we can sort of show that this is not going to be a shortest path. How can we show that? Basically, it's really just very intuitive. You can really just delete the entire cycle over here, right? Delete the second step over here, right? This is over here, right? So why is that? Because this is a cycle. So let me just use this a little bit larger, right? Because this is a cycle, and we know that this cycle, the cycle here is not negative, right? So basically the cycle here, it's either 0 or positive, right? So in case like it's 0 or in case it's positive, then we can really directly remove this cycle and just remove that and get the path that's from 1 to from V to this node, and use the path 1 and then use path 3 to T, right? So we can sort of delete this cycle. And after we delete the cycle, and because this cycle has positive weight, we will only get a path that's going to have a smaller weight sum, right? In case this cycle is 0, then basically we remove this cycle. It's not going to impact the path weight. So we are able to produce another simple path that's based on the non-simple path that's returned by this algorithm. So in either case, we are always able to find a simple path that's connecting between two nodes, right? And another observation is that if I look at all possible simple paths, right? So let me just erase everything here, right? So I do have a question on here, right? So if I just look at all the simple paths, right? So what is the max possible number of edges in this in a simple path? Right. So it's really just that by the pigeonhole principle, the number of edges is going to be less than or equal to n, right? So sometimes we can also count the number of nodes, right? So just imagine that if I have a graph, if I have a path, right? Somehow this is a path, and my path consists of a total number of if I just count the number of nodes. Right, so let me just use this one. If I count the number of nodes on a path, and then if the total number of nodes is larger than or equal to n plus 1, this really just implies there's exists a node that appears twice. Right. So when there's a node that appears twice in this cycle, in this path, that basically means that this is not simple, right? not simple, right? So basically, that this kind of lemma really just said, in case there exists no negative cycle, then then we can always find the shortest path that's simple. And when the shortest path is simple, the number of edges here is really just less than n minus 1, and the number of nodes is also less than n. So now let's move to the actually so using the dynamic programming to solve the problem, right? So in fact, we are really facing two interrelated problems that we want to solve. The first problem would be the shortest single destination shortest path problem, right? So basically, in this problem, basically we can assume that if we are given a graph that doesn't have any negative cycle, and can you find the shortest path connecting from S to T, right? And and the second one would really just be the negative cycle detection problem, right? So given a directed graph, can you detect a negative cycle, right? So they are sort of interrelated in in a particular in two ways. The first way is that if I really want to solve the general shortest path problem, then basically what I need to do is the first to detect the negative cycle, right? Detect negative cycle. After I detect the negative cycle, I sort of need to check whether the problem is well defined, right? So well defined, like in case like we have the scenario we mentioned just now, that if it's I move from S to T, there's somehow some node V that's associated with a negative cycle, then it's impossible to find the shortest path between S and T. Then after we check the well-definedness, then we can call the algorithm for the first problem, right? To solve the problem without the negative cycle. Next cycle, right? So this is the relationship between these two problems. So we in really just if we really want to solve the general shortest path problem, we do need to invoke the algorithm for the second problem and solve the first problem. And that's the first relation. And the second relation is more interesting. It turns out that if we just modify this algorithm a little bit, we are actually able to directly detect the negative cycles, right? So these two problems are effectively the same, but in so basically in general, we are really just run one piece of code. At the end of the time, the code will either output a negative cycle or output the shortest path, right? So those are the really just the relationship between these two problems. And really just notice that here we are looking for a single destination. So usually we look for the single source, right? Single source, shortest path, right? So basically we are looking for the from if I'm given an S, I want to find the shortest path connecting between S to all other nodes, right? But here, it's really just a single destination. If I given the destination T, am I able to find the shortest path that's ending at the T, right? So basically, there's it's really this is just a definitional issues, right? Somehow when we run the DP algorithm, we are actually able to